Okay, time for our second big chunk of chemical change, and that is equilibrium. So once again, we're going to go through some of the key theory points. I'll just give you a quick summary of things that you need to know, and then as a separate video, I'll do a worked example for you. So equilibrium, what's it all about? Well, unlike the picture that you might have in your head of a set of scales or a seesaw or something, chemical equilibrium is slightly different. The seesaw we'd imagine in equilibrium when it's stopped. But chemical equilibrium is what we call dynamic equilibrium because it's actually still on the move and yet balanced. So it's a little bit of a weird concept to get your head around. Let's have a look at a classic example which comes up all the time, which is the basis of the Haber process, where we make ammonia. Nitrogen and hydrogen being combined to form ammonia molecules, which in turn can then break down and then form nitrogen and hydrogen again. So in order to have a chemical reaction where there's equilibrium, it has to be a reversible reaction. It has to be able to go both ways. And this dynamic equilibrium occurs basically when those two are the same speed. So the rate of the forward reaction, in other words, the rate at which we're producing ammonia, is exactly the same as the rate at which the ammonia is breaking down. And so the numbers stay the same on both sides, even though the chemical reactions are happening. And that's where the balance is. So it's dynamic because the reactions are occurring, but it's balanced because we've reached a state where the amounts don't change on either side. That's dynamic equilibrium. Now, often we have to answer or explain how a certain change will affect the state of the equilibrium, and right at the heart of that is a wonderful principle came up with by a chap called Monsieur Chatelier, Professor Chatelier. Now, basically, his principle is just rebellious. I think it's this sort of French rebellion in him. I'm not quite sure it is, but it's just like teenagers and bed. When they're not in bed, they don't want to go to bed, and when they're in bed, they don't want to get out of bed. And that's the basic same principle of Le Chatelier's principle. Now, there's nothing wrong with that. It's just healthy rebellion. It's a good thing. And as it is with Le Chatelier, when you heat the system up, well, what does it want to do? It wants to cool it down. And when you decrease the pressure, it wants to increase the pressure. And when you increase the concentration of X, it wants to decrease the concentration of X. So that Le Chatelier's principle explains the reaction of the system to those types of changes. Now, putting it into words can be a bit more challenging. And scoring the marks and so on. So I'm just going to give you a little acronym, DLFR, and I'll show you how to remember that at the end. But DLFR is a nice little 4-step process to be able to explain how Le Chatelier's principle helps us to understand a particular disturbance. So the first thing to do is literally to reiterate what the disturbance was. So let's have a look at this example at the top here. If we heated that particular system, how is that going to affect the position of equilibrium? So first thing you would do is to say, well, the change, the disturbance, the thing that we're focusing on, was to heat it. So you literally just sort of be reiterating what the question is saying. Okay? You can mention the fact that because it was heated, both reactions are going to be going faster. Okay? You can mention that at that point. Why so simple? Why when the question is told us it's heating it up, why do we have to say it again? Well, the reason I suggest that is because it sets you up beautifully for the second point, which is where we start to bring in Le Chatelier's principle, which is exactly the opposite of whatever the disturbance was. Okay, so if the disturbance was that it was heated, then according to Le Chatelier's principle, it's a nice little phrase, I'll summarize it here, according to Le Chatelier's principle, and then you just have to state whatever the opposite is. So the mixture is heated, therefore, according to Le Chatelier's principle, the system is going to try and cool itself down. Okay, that is the exact opposite. So you're kind of halfway through the argument and you haven't even had to really turn your brain on. You've just said what the question said and then said the opposite of what the question said. Now, this is where you have to start thinking a little bit, because F is now where we work out which one is therefore going to be favored. Is it going to be the forward reaction or is it going to be the reverse reaction? That is the big question. Forward or reverse. And to do that, we're going to need a little bit more information than I put on the board right now, because if we're talking about heat, there's one piece of info you need, and that is the delta H. and in this case, delta H is negative. Now that is referring to the forward reaction. If you remember from the rates discussion, a negative delta H means that the forward reaction is in fact exo. Put that there for your memory. Therefore, it means the reverse reaction is endo. So let's run through the process. Disturbance was the system was heated. According to Le Chatelier's principle, it's going to try and cool itself down. Therefore, it's going to favor an endothermic reaction, which is the reverse reaction. Okay, so that the endo, that little mention, also brings in the very important Y factor. So that's where the chemical knowledge comes in. For pressure, you're looking at moles of gas. How many moles of gas? If we put it under pressure, it wants to alleviate that pressure by producing less moles of gas, so it's going to go this way. It's going to favor the forward reaction. Concentration, if we suddenly increase the amount of hydrogen, well, it's going to want to use up the hydrogen, therefore, once again, favoring the forward reaction. So that's just a quick overview of some of the favoring ones. And then to wrap it all up, you just mention the result. What is the outcome? And the reason I've included that as a separate point on its own is because often the question asks you something in particular. How does this affect the yield of ammonia, for instance? So let's just quickly run through this. The system was heated. It's going to try and cool itself down by favoring an endothermic reaction, which is the reverse reaction, which in fact results in less ammonia being produced. That would be a great example. If they don't ask you for yield or something, you could perhaps just mention the concentration of products or something along those lines. So that's DLFR. It's a nice little four-step way of getting your marks. And a great way to remember DLFR is it's actually not a bad description of Le Chatelier himself. But you do have to say it with the correct accent. Die little French rebel. There you go. He's definitely French, definitely rebellious. I don't know how big he was, but that'll help you to remember DLFR. That's a nice way to explain equilibrium. Okay, let's have a quick look at graphs in light of Le Chatelier's principle. There's a lot to go through here, but again, I'm just going to zip through them, and through practice, you will consolidate the knowledge. I guarantee. Even if it feels like a bit of a blur at the moment. And that's true for all your topics, by the way, just a bit of encouragement. When you're starting something, it can seem so distant and so out of reach, but it will begin to make sense, don't worry. There's two types of graphs when it comes to equilibrium graphs. One is a concentration, or moles perhaps, but it's something to do with an amount on the y-axis, and the other one is to do with rates. Now, I'm going to do an example of an amount one. The rates one, though, has just got two lines because it's representing the forward reaction and the reverse reaction. And they always meet in the middle. You show them very close to each other because the rate of the forward has to be equal to the rate of the reverse. The amounts one, I think we're going to use a similar example, our ammonia one, just because it's so common. There will be as many lines on the graph as there are components in the reaction. So we could have nitrogen, hydrogen, and ammonia, something like that. And that could be the concentration of each of those things, or just the moles. They may just give you moles. Okay, and it's versus time. It's telling you the story of how that changed as time went by. So let's have a quick look at some of the changes that we might get. Let's say at time T1, there was an increase in the concentration of nitrogen. Now what happens is, we know that according to Le Chatelier's principle, things are going to shuffle and shift around, but only one of them will do that radically when it's a change in concentration. So the nitrogen spikes up like that. The other two, well, let's just focus what happens after that change. According to Le Chatelier's principle, we've increased it, it's going to try and decrease it, so we're expecting this to sort of come down like that and reach a new equilibrium. I hope you guys are all happy with the fact that equilibrium was first reached somewhere around here where the lines became flat. Okay? Now let's think of what happens to the other two lines. If the N2 is being used up, that means that H2 is also being used up. Now if you note, I've made the changes on the H2 line slightly bigger than the N2 line, and that's because of the molar ratio. I haven't done it perfectly, and your examiner's not expecting you to do it perfectly, but it's worth bearing in mind that if it's a 1:3:2 ratio, then the changes should be 1:3:2. As you can see, I haven't got it perfect, but that's just a little point to bear in mind. Ammonia, on the other hand, will be produced, and so that line is actually going to go up. But it doesn't change immediately, just like the hydrogen. It didn't change immediately, it slopes instead of spiking. All right. Let's have a look at another change at another time, T2. Let's say the temperature was increased. Okay, we just talked about the fact that increase in temperature is actually going to favor the reverse reaction. So we're going to end up with more hydrogen and nitrogen being produced, but none of them immediately if it's an increase in temperature. So this is going to slope up. I'm going to run out of room here, so I'm going to have to reduce my time frame, but that's going to be a bit more, something like that. And the ammonia is going to be used up. So change in temperature, so this is a change in temperature, this was a change in concentration, and let's lastly have a quick look at a change in pressure. Change T3, let's say, and this makes us blue, change in pressure. Well, a change in pressure, actually these are all gases. So if we say increase the pressure, then all of them should just go up a little bit, whether it's a spike or maybe a step, but they all should go up because we've squished them into a smaller space and therefore their concentration goes up. And then they'll be affected by Le Chatelier. So we've increased the pressure, it's going to favor the forward, so therefore more ammonia is going to get produced, it's going to go up, and the other guys are going to come down. Okay. So that's a quick example. I hope that makes sense. Repeat, rewind if you want to go over that one again. We will do another worked example with some slightly different things. The rates graphs, I was going to talk them through. Obviously, it looks fairly similar. They come together and they'll be equal to each other here. When there's an increase in concentration, that's going to up the rates, but only of the forward one immediately, and the other one then just adjusts to meet it. With the pressure and temperature changes, there will be a sudden change to both, but one more than the other. So whichever one is favored will have the biggest spike, and the other one will have just a little step, you could call it. Okay. What's the function of adding a catalyst? Well, the catalyst doesn't change equilibrium at all, so these graphs would actually just continue straight along. But the rates thing does something quite interesting. Both lines would go up together and then continue. So neither is favored, but they both go faster. There you go. That's graphs. Last thing to look at with equilibrium is KC calculations. Now this little section is fantastic. It's marks on a plate for you. They are so easy. They're nearly always 7 to 9 marks worth of calculations and so on, and they're really not hard once you get the hang of them. So there's some fantastic methods. There's a Rice method, or Shrek, sometimes people call it, where it just organizes the information nicely into a table. So I'm just going to draw up a table quickly for you. Okay, there we go. That was a quick one there. This is a... Okay, there we go. It was a quick one there. So that is a sort of the basic layout of how you do the table with your ingredients across the top there, and then your various different things down the side. I've used this as a rice table where we start with the ratio at the top, then we look at what we start with, the initial, the change, and what we end up with at equilibrium. The Shrek table would be looking at that start, reacted, end or equilibrium, and then you can add in the concentration down here. So my rice table can become rice crackers or rice cakes if you want. So let's take a simple example. Let's say in a particular experiment there were 5 moles of nitrogen and 10 moles of hydrogen put into a sealed container, and at the end of the experiment we had 1 mole of hydrogen left, and it was a 2 decimeter cubed container. What is the Kc? So we put in the values that as I've done already. There was 5 and there was 10. We're not told anything about ammonia, so we can assume it's 0. There's 1 mole of hydrogen at the end, so then you can put that there. Then the first rule that we can make use of these rice tables is basically that I plus C must give us E. Whatever we started with at the beginning plus whatever changed is what we have at the end. Makes sense. So 10 something gives us 1. So the something must be minus 9 using a bit of algebra. Okay? So we must have used up 9. Now once you've got one thing in the middle row, so that's rule number 1. Rule number 2 is that the ratio line and the change line must be in the same ratio, the same proportions. So the R and the C go together. So we know it's a 1 to 3 to 2 ratio. This is 9, looking at just values as opposed to signs for now. 3 to 9 is a ratio of 3, so therefore we can multiply that by 3 as well. And 2 multiplied by 3 is 6. So the ratio of 1 to 3 to 2 is the same as 3 to 9 to 6. I hope you get that. Okay? We are using up these two, so they will be minus, and we're making that so that is going to be plus. Then we can apply this rule again. 0 plus 6 is going to give us 6. 5 minus 3 is going to give us 2. And those are going to be our end molar amounts. To work out the concentrations, just put them over the moles. Put them over the volume of the container. 6 over 2 equals 3. So those are the moles per decimeter cubed. And then we move on to the Kc calculation, which you probably are happy with the concept that it's products over reactants. Never write that down because it's just a helpful tool for us to think of which way it goes. Any correct Kc expression must come from the balanced equation. So it's the products, which is the concentration of NH3. It is a gas, so we can use it. Remember, solids and liquids are left out. NH3, and we put it to the power of the coefficient. And similarly, we can use the nitrogen, which doesn't have any power, and the hydrogen, which is cubed. Excuse me. Okay, so that is our expression. And then we would then plug in the values. So NH3 is 3 squared over N2, which is 1 times H2, which is 0.5 to the power of 3. Okay, so that's basically 9 multiplied by 8, which is equal to 72, I think. So that is a pretty high Kc. And just as a matter of interest, what does Kc tell us? Well, because it's the whole thing of products over reactants, let's put some big brackets over here. If we've got a big number like that, it means that the concentration of products is much higher than the concentration of our reactants. In other words, the reaction has progressed quite far. On the other hand, if it hasn't got very far, it's going to be a very small number. In fact, it's going to be less than 1. And if it's about 1, then it's around about in the middle. So a big number like that means, yes, we've got a great yield. It's pushed on quite far. Okay, well, I hope that's helpful. That is a bit on Kc. I think those are the key facts that you need to know. Time for a worked example.